Hello, today we are going to perform a self-study session on chemistry. So we are going to take a pre-test. Okay, so use this diagram to answer the following 7 questions. This looks like a hydrocarbon, alpha X, Y, Z, beta, delta, Y. So the first question is there are dash carbon atoms in the parent chain. It is called dash. So if I remember correctly, we have to choose the longest possible parent chain and then look for the specific groups. So the longest possible parent chain, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the longest possible parent chain is of 6 carbon. So it should either be 6 pentane or 6 hexane. Let's go with 6 hexane. Numbering of this molecule will begin at carbon. So I think we will begin with alpha because I have selected this 1, 2, 3, 4, 5, 6. Begins with alpha, ends with delta. So let's select alpha. Use this information along with previous diagram to answer the following 5 questions. There are branches at carbons X, Y, and Z. X, Y, and Z. Okay. X, Y, and Z. The branches at carbon X is are called. The branches at carbon X. So I think it is called as pen. I think it is called as methyl propyl. There is a type of branch that is common between carbon X and Z. What is called? What is it called between X and Z? X and Z. So this is basically C and C. C, C, C. Carbon, carbon, carbon. So I think it is called as. Uh, I think it is called as a methyl bond, if I remember correctly. So we'll select methyl. Which carbon is able to make another bond? Which carbon? I think Z. What is the IUPAC name of this molecule? IUPAC name. Hmm. I'm not sure about that. What is the IUPAC name of this molecule? Let's go with 6. 6 hexane. I think. 6-hexane ethyl, uh, ethyl, and this is a methyl. Ethyl 1, 2, 3. I think at 3 and 4. 3 and 4. I think it is 3 ethyl 3, 4 methyl hexane. The addition of a methyl group onto carbon dash would cause a change only to the name of the parent chain. So it is asking about the, the named carbon atom on which if we add a methyl group, then that would change only to the name of the parent chain. So I think it would be the last in the parent chain, that is from alpha XYZ delta. If we add a delta, so let's go with delta. Which of the following molecules is not an organic molecule? Tetrafluoromethane, tert butoxide, hydrogen cyanide, and benzene. So I think benzene is an organic molecule. Cyanide is also, I think, a poisonous substance, extremely poisonous and extremely deadly substance. Tert butoxide and tert fluoromethane, tetrafluoromethane. Hydrogen cyanide, I think, does not contain anything from the organic chemistry. It is an individual substance that is highly poisonous. So let's select hydrogen cyanide. Next, how many valence electrons are present in butane? How many valence electrons are present in butane? So I think butane structure, if I remember, present in butane. Fun. So butane is basically, I think, if I remember, it is C4H10. So basically, four valence electrons from one carbon. So four carbon will provide 16 and H10. So each hydrogen has only, I think, one valence electron. So it will be 16 plus 10, 26. So it is 26. Which element has the same number of electrons as butane has valence electrons? So if the number of valence electrons in butane is 26, we have to look for the element which has the same number of electrons as butane. So 26, we in periodic table 26 I think is iron, if I remember correctly. Iron is, I think, yeah, the 26th element. Okay. Which of the following functional group is most likely to emit a pleasant sweet smell? Present sweet smell. Hmm, I'm not sure about that. Can you answer to the previous question? Participate in hydrogen bonding, why or why not? Can you answer to the previous question? Participate in hydrogen bonding, why or why not? I think there is a hydrogen atom present, so as I think here hydrogen is present attached to the oxygen, and this hydrogen can dissociate. So this has hydrogen attached to the oxygen and associate or dissociate. So it might dissipate, yeah, in the hydrogen bonding. Which molecule will have the highest boiling point? Okay, highest boiling point. So highest boiling point would implicate that the structure of the chemical that is present, it should have a very strong bonding. Because boiling point would require it to reach it to a temperature high enough to break that strong bond. So higher the bonding power between the atoms, higher will be the boiling point. CH3COOH, CH3Cl. This is a chlorocarbon. C- I think this has OCH3, methyl or something. CH4 is alkane. So I think oxygen-oxygen bonding is very strong because I think oxygen loves electron. They are electrophilic. So maybe this. How many hydrogen atoms does an alkene with n carbon atoms have? So I think there are alkane, alkene, and alkyne, and all have their basic formulas of 2n plus 2, 2n, and 2n minus 2. So I think the formula, if I remember correctly, is CnH2n. So this will be 2n. Use this information to answer the following 5 questions: molecule name and boiling point. Ethanol 78.4, 1-heptene 94, ethanoic acid 117.9, decane 174.1. Which molecules have London dispersion forces? I think London dispersion forces are extra kind of atomic forces that actually provide weak bonding between the molecules, if I remember correctly. So, ethanoic and decane. Ethanoic and decane. Hmm. Let's choose ethanol, 1-heptene, and ethanoic acid. Now assume each substance is a liquid at room temperature. Which of these molecules can mix with water? Mix with water. So I think ethanol can easily mix an ethanoic acid, and organic acid can also mix with water at room temperature. So let's select ethanol and ethanoic acid. Why can they mix with water? So because ethanol is an alcohol uh, which has affinity for water. I think that is the hydrogen present in the water, and ethanoic acid is an organic acid which are known to be hydrophilic, which are known to be hydrophilic. Despite that decane does not have a permanent dipole, it is boiling point its boiling point is much higher than ethanoic acid. Why? Mm. Why can they mix with water? Because ethanol is an alcohol which has affinity for water. Hydrogen and ethanoic acid is organic acid, which are known to be hydrophilic. Okay, yeah. Despite that, decane does not have a permanent dipole. Its boiling point is much higher than ethanoic acid. Why? Hmm. I think ethanoic acid has only two carbon atoms, and decane has one, 8, and 1. That is 10. Since it has having more number of carbon atoms, then I think that is why its boiling point is automatically increased. S- Yeah, because decane contains the most carbon atoms. I think this is the reason. Where would you expect methanol to place in this list? Methanol. I think methanol is only a single carbon molecule, so it should be below ethanol or above ethanol. Let's go with above ethanol. Use this diagram to answer the following four questions. So this is a pentagram with alpha, beta, gamma. This is a pentagon, sorry. 1, 2, 3, 4, 5. Alpha, beta, gamma. I think this is pentane. The chemical name might be pentane. The addition of a methyl group to which carbon would not produce a molecule with a side chain. Hmm. So this looks like a pretty symmetric structure. So I think all of them would produce a molecule with a side chain. The addition of a methyl to which carbon atom, the addition of a methyl to which carbons would produce the same molecule. I think all additions produce the same molecule. How many valence electrons are present in this molecule? So this is 1, 2, 3, 4, 5. 5 carbon atoms, so 5 into 4 is 20. 20 plus 1, 2, 3, 4, 5. I think 1, 2, 3, 4, 5. So there are two hydrogen atoms. So I think it will be around 5 into 4 is 20 plus 10. Yeah, so I think 20 plus 10 is 30. What is the maximum number of propyl groups that can be added to carbon alpha? Maximum number of propyl groups that can be added to carbon alpha. I think 1. So the electrons in a benzene molecule are not fixed on one atom. They are. Okay. The electrons in a benzene molecules are not fixed on one atom. They are. I think they are delocalized. That is why they continuously move in the structure of the benzene and are able to perform chemical reactions, as per my knowledge. An acidic flavor compound has been discovered. Okay, an acidic flavor compound has been discovered. It is naturally dissolved in an organic solvent. That is, it is non-polar. It does not have any natural odor or color. In the lab, you are presented with 5 vials that may contain the flavor compound. How will you attempt to detect its presence? An acidic flavor. Okay, so there is an acidic flavor compound and it gets dissolved in an organic solvent that is non-polar. Okay. It does not have any natural odor or color. In the lab, you are presented with 5 vials that may contain the flavor compound. How will you attempt to detect its presence? Add orange dye. Artificial orange dye will absorb it into an acidic compound. Add water. An organic compound will readily dissolve in water. Titrate using HCl. Hmm. I think since it is an acidic flavor and NaOH is a alkaline in nature, I think it is basic in nature. So we will titrate using NaOH to neutralize the solution. Let's see. We have performed the test now. Let's submit. Let's view our score. Okay, so we have scored 16 out of 25. Okay, so now what we are going to do is we are basically going to Google search the questions that I have performed incorrectly and try to get an idea. So, okay, first we need to use this image. So let's take a screenshot. Yeah, okay. And the first question that we did wrong was the branches at carbon X is are called. So let's open Google search. Let's upload an image. Yeah, this is the given image. Yeah, now let's copy paste the question. The branches at carbon X are called. Hmm. So as we can see, I perform the search on the given image and the branch at. So let's modify the search a little bit. The branch at carbon X is called. Hmm. I think in the visual search, oh, no such image is coming up on the visual search. Okay, the branches at carbon X is are called. Mm. Correct answer is methyl cyclopropyl. So let's Google this up. So let's try to find out what is the structure of methyl cyclopropyl. Methyl cyclopropyl. This is the ACS publication. Okay, let's try to. Okay, so the given structure here at X, so there is this triangle-like thing. So I think that triangle-like thing with the branch is called as cyclopropyl. This is cyclopropyl methyl ketone. Okay, got it. Got it. So that is called as methyl cyclopropyl. I think this is the methyl group and this is the cyclopropyl group. Okay. The second question that we got wrong was which carbon is able to make another bond? I chose as Z. The correct answer is Y. The correct answer is Y. Hmm. So we will search it up. Hmm. As we can see, the exact image is not coming up on the search. So I think we will move on to the next question. What is the IUPAC name of this molecule? So the IUPAC name of this molecule is okay, 2-cyclopropyl 3-ethyl 2, 4, 4 trimethylhexane. So this is a quite complicated name. So let's search this thing. 2-cyclopropyl 3-ethyl 2, 4, 4 trimethylhexane. Okay, so this is the structure of one part that is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is the structure of 2,4,4 trimethylhexane. 2-cyclopropyl was the triangular structure. So I think this is the triangular structure, that is methyl cyclopropyl, and then this part is the 2,4,4 trimethylhexane. Okay, so I wrote as 3-ethyl 3,4 methylhexane. Okay, got it. So our next question is, which of the following functional groups is most likely to emit a pleasant sweet smells? The correct answer is RCOOR dash. So let's Google this question. Mm. Okay, so fats and vegetable oil are esters of long chain fatty acids and glycerol. Esters of phosphoric acids are of the utmost importance to life. The correct answer was, I think, esters. That chemical structure, this chemical structure represents ester bond. So, summary is a carboxylic acid is an organic compound that contains the carboxyl functional group. An ester has an OR group attached to the carbon atom of a carbonyl group. Okay, so this is important. Has an OR group. Yeah, as we can see, I think this is the OR group. Ester occurs widely in nature and generally have pleasant odors and often responsible for the characteristic fragrances of fruits and flowers. Got it. Okay. The next question that we got incorrect was, can you answer to the previous question? Participate in hydrogen bonding, why or why not? I chose as hydrogen attached to oxygen can dissociate or associate, so it might be participating in the hydrogen bonding. No, there are oxygen atoms, but they are not bonded to any hydrogen atoms. Okay, so this ester group does not have any bonded hydrogen atoms. That is why they cannot participate in hydrogen bonding. So this is the correct answer. Okay, got it. Now, next question that we did wrong was, which molecules have London dispersion forces? So first, let's exactly look what exactly is this London dispersion force. Let's search what is London dispersion forces. London dispersion forces, LDF, also known as dispersion forces, London forces, instantaneous dipole induced dipole forces. Fluctuating induced dipole bonds, or loosely as van der Waals forces, are a type of intermolecular force acting between atoms and molecules that are normally electrically symmetric. That is, electrons are symmetrically distributed with respect to the nucleus. They are part of the van der Waals forces. The LDF is named after the German physicist Fritz London. They are the weakest of the intermolecular forces. Okay. So the idea is that London forces are basically the forces that are present between the atoms of a molecule that are electrically symmetric. That is, the distribution of electrons is symmetric. The electron distribution around an atom or molecule undergoes fluctuation in time. These fluctuations create the instantaneous electric fields which are felt by other nearby atoms or molecules. The net effect is that the fluctuations in electron positions in one atom induce a corresponding redistribution of electrons in other atoms. While the London dispersion force between individual atoms and molecules is quite weak and decreases quickly with a separation R like 1 upon R raised to the power 6. In condensed matter, liquids and solids, the effect is cumulative over the volume of materials or within the organic molecules, such that linear dispersion forces can be quite strong in bulk solids and liquids and decay much more slowly with distance. For example, the total force per unit area between two bulk solids decreased by 1 upon r cube, where r is the separation between them. Okay, so this statement basically means that if we keep two bulk solids together and separate them by a unit distance, the London force between them decreases by a factor of 1 upon r cube. Okay. The effect of London dispersion forces are most obvious in systems that are very non-polar. That is, that like ionic bonds such as hydrocarbons and highly symmetrical molecules like bromine at a liquid at room temperature or iodine, a solid at room temperature. In hydrocarbons and waxes, the dispersion forces are sufficient to cause condensation from the gas phase to the liquid or solid phase. Sublimation heats of example hydrocarbon crystals to reflect the dispersion, interaction, liquefaction of oxygen and nitrogen gases into liquid phases is also dominated by attractive London dispersion forces. Okay, got it. The next question is, why can they mix with water? Assume each substance is a liquid at room temperature. Which of these molecules will mix? So I chose this because ethanol is an alcohol and ethanoic acid is an organic acid. So I thought that they might mix with water at room temperature. So the correct reason for this is that they both can participate in hydrogen bonding. Water is also able to do so. That is why like dissolves like. Okay, do so. Hmm. Let's Google this question. The exact question is not available, but ethanol and ethanoic acid. Let's modify the question. Why do ethanol and ethanoic acid mix with water at room temperature? Ethanol has a lower boiling point than water, so it evaporates first. Okay. Okay, so there is a modified question called, which is what reacts at room temperature with ethanol and also with ethanoic acid. So one has responded ethanoic acid reacts with ethanol in the presence of concentrated sulfuric acid as a catalyst to produce the ester, ethyl ethanoate. The reaction is slow and reversible to reduce the chances of the ester is distilled off as soon as it is formed. Answer is esterification reaction. When organic acid react with alcohol, it forms ester and water. Reaction is known as esterification reaction. This reaction is reversible and it is also okay. This reaction takes place in the presence of acid, catalyst, that is diluted sulfuric acid, H2SO4. Okay, let's move on to the next question. Okay, what is the maximum number of propyl groups that can be added to carbon alpha? Maximum number of propyl groups that can be added to carbon alpha. So let's first Google search this image. Mm, I think this is a pentane. So yeah, this is a pentane. So the question is, what is the maximum number of propyl groups that can be added to carbon alpha? So uh, carbon alpha. So let's search this question. Carbon alpha in a pentane. Hmm. There is no exact search. Okay. The electrons in a benzene molecules are not fixed on one atom, they are. So I wrote the answer as delocalized, which is the correct answer because the electron in the benzene keeps moving in its own structure. That is why it is called as a delocalized electron. So that is actually a correct answer, but the D is capital, so that is why it has not exactly matched with the correct answer due to the spelling, due to the capital notation used. Okay. So this was the pretest that was performed by me, in which I got 16 out of 25. Okay, so now we will study a bit about some questions that we need to search. So uh, let's search about some questions like what are the IUPAC rules on naming the Straight chain alkanes. Straight chain alkanes. So let's go to chemistry library text and let's read. Naming alkanes by Stephen Farmer, Kenepol, Sharrett, Cunningham, and Soderbergh. After completing this section, you should be able to provide the correct IUPAC name for any given alkane structure. Kekulé condensed or shorthand. Draw the Kekulé condensed or shorthand structure of an alkane given its IUPAC name. Okay. IUPAC system of nomenclature. The IUPAC system of nomenclature aims to ensure that every organic compound has a unique, unambiguous name, that the IUPAC name of any compound conveys the structure of that compound to a person familiar with the system. One way of checking whether the name you have given to alkane is reasonable is to count the number of carbon atoms implied by the chosen name. For example, if you named a compound 3-ethyl-4-methyl-heptane, you have indicated that the compound contains a total of 10 carbon atoms. 3-ethyl-4-methyl. Okay. Of 10 carbon atoms, 7 carbon atoms is the main chain. Two carbon atoms in an ethyl group and one carbon atom in a methyl group. If you were to check the given structure and find 11 carbon atoms, you would know that you had made a mistake. Perhaps the name you should have written was 3-ethyl 4,4-dimethylheptane. When naming alkanes, a common error of beginning students is a failure to pick out the longest carbon chain. For example, the correct name for the compound shown below is 3-methylheptane, not 2-ethylhexane. Okay. Following table lists the IUPAC names assigned to simple continuous chains alkanes from C1 to C10. A common "-ane" suffix identifies these compounds as alkanes. Okay, so this is the generalized version. If the name ends with "-ane", it is an alkane, and we have to select the longest possible carbon chain, that is the parent chain. Longer chain alkanes are well known and their names may be found in many reference and textbooks. The name methane through decane should be memorized since they constitute the root of many IUPAC names. Fortunately, a common numerical prefixes are used in naming chains of 5 or more carbon atoms. Methane CH4, ethane C2H6. Okay, propane C3H8, butane C4H10, pentane C5H12. The given structural formulas: heptane, hexane, octane, nonane, decane, C6H14, C7H16. So alkane has a general formula of CnH2n plus 2 because each hydrogen, the number of hydrogen is 2 more than the number of carbon. So CnH2n plus 2. That is the, yeah, so these formulas all fit the CnH2n plus 2 rule. This is also the highest possible H by C ratio for a stable hydrocarbon. Okay. Since the H by C ratio in this compound is at maximum, we call them saturated with hydrogen. Okay. Beginning with butane C4H10 and becoming more numerous with larger alkanes, we note the existence of alkane isomers. For example, there are 5 cis-6H14 isomers as shown below as abbreviated line formulas A through E. Although these distinct compounds all have the same molecular formula, only one A can be called hexane. How are we then to name the others? CH3 methyl, C2H5 ethyl, CH3, CH2, CH2 propyl, CH3, 2, CH isopropyl. So CH3, CH2, CH2. So that was cyclopropyl in one of our question. So okay, cyclopropyl, got it. IUPAC rules for alkane nomenclature. Find and name the longest continuous carbon chain. Okay, identify names groups attached to this chain. To this chain. Okay, so we have to identify whether it is methyl, ethyl, propyl, isopropyl, butyl, isobutyl, sec-butyl, tert-butyl, alkyl. Design the location of each substituent group by an appropriate number and name. Assemble the name listing groups in alphabetical order. The prefixes di, tri, tetra are used to designate several groups of the same kind, are not considered when alphabetizing. Example: A is hexane, K-methylpentane, 2-methylbutane, 2,3 dimethylbutane. Okay. Halogen groups. Alkyl groups. Okay. Methane, ethane, propane, butane. Butane is C4H10, pentane is C5H12. Let's search the structure of pentane. So this is the structure of pentane. Okay. In pentane. One, two, three, four, five. Got it. So let's look at the let's look at the physical characteristics of organic functional groups. Uh, Physical characteristics of organic groups. Hmm. Let's open the Khan Academy site. Functional groups. Large biological molecules are generally composed of a carbon skeleton made up of carbon and hydrogen atoms and some other atoms including oxygen, nitrogen, or sulfur. Often these additional atoms appear in the context of functional groups. Functional groups are chemical motifs or patterns of atoms that display consistent function, properties, and reactivity, regardless of the exact molecule they are found in. Biological molecules can contain many different types or combinations of functional groups. And a molecule's biomolecule particular set of groups will affect many of its properties, including its structure, solubility, and reactivity. The only hydrophobic group below is methyl, that is CH3 group, which is non-polar. Okay, so it does not react with water. The remaining six functional groups in the table all have varying degrees of hydrophilic character. Okay, hydroxyl is polar, methyl non-polar, carbonyl is polar, carboxyl acidic, amino is considered as basic, phosphate is considered as acidic, sulfhydryl is considered as polar. The table above the letter R is used to represent the rest of the molecule that a functional group is attached to. Okay. Hmm. So in the name of physical characteristic of organic functional groups, only its affinity for water was shown. That is whether it is hydrophobic, hydrophilic, or whether it is acidic or basic. So let's search the intermolecular force types. Intermolecular force types. Let's open the site of Byju's. What exactly are the intermolecular forces? Intermolecular forces, often abbreviated to IMF, are the attractive and repulsive forces that arise between the molecules of a substance. These forces mediate the interaction between individual molecules of a substance. Intermolecular forces are responsible for most of the physical and chemical properties of the matter. Okay, so this is an important point. Intermolecular forces are responsible for most of the physical and chemical properties of the matter. Forces also exist between the molecules themselves, and these are collectively referred to as intermolecular forces. Intermolecular forces are mainly responsible for the physical characteristics of the substance. Intermolecular forces are responsible for the condensed states of matter. The particular making up solids and liquids are held together by intermolecular forces, and these forces affect the number of physical properties of matter in these two states. So the basic idea I think is that if the intermolecular forces are strong, then the boiling point or the melting point of that respective molecule is going to be higher. If it is weaker, then they will also have a weaker boiling point or a melting point. Types of intermolecular forces. Okay. By comparing the boiling points of different substances, we can compare the strengths of the intermolecular forces. This is because the heat absorbed by the substance at its boiling point is used to break these intermolecular forces and to convert the liquid to vapor. Okay, more the intermolecular force, more the boiling point and melting point, and vice versa. Less force means less intermolecular force. Okay. The intermolecular forces depend upon the following interactions: dipole-dipole, ion-dipole, ion-induced dipole, dipole-induced dipole, dispersion forces or London forces. So I think these are actually the five types of the intermolecular forces. Dipole-dipole. Dipole-dipole interactions are attractive forces among polar molecules. Polar molecules have permanent dipoles that are formed due to differences in the electronegativities of the atom that are associated with a covalent bond. The partially positive portion of one molecule is attracted to the partially negative portion of another molecule. Example, dipole-dipole interaction occurs in HCl molecules. Chlorine is comparatively more electronegative than hydrogen and it therefore acquires a partial negative charge, whereas hydrogen acquires a partial positive charge. The dipole-dipole interaction then takes place between the HCl molecules. Okay, ion dipole interactions. These interactions are similar to dipole-dipole, except for the fact that they arise between ions and polar molecules. Okay, so these occur between ion and polar molecule. Example, when NaCl is mixed with water in a beaker. Okay, so I think here NaCl will provide the ion and polar molecule will be the water one. In polar, H2 molecules are attracted to the sodium and chloride ions in the beaker. The strength of this interaction depends on magnitude of the dipole moment, size of the polar molecule, and the size of the charge of an ion. So I think these forces basically act as vectors because they have both a direction and a magnitude. they must be acting along a particular line in their field that they create due to their charge. Ion-induced dipole interactions. In this type of interaction, a non-polar molecule is polarized by an ion near it. The non-polar molecule, upon obtaining a charge, behaves like an induced dipole. Okay, so this is an important point. This interaction between an ion and an induced dipole is known as ion-dipole interaction. Ion and ion-induced dipole interaction. Fourth one is dipole-induced dipole interaction. These interactions are similar to ion-induced dipole interactions. However, the differentiating factor is that non-polar molecules are transformed into induced dipoles due to the presence of a polar molecule nearby. Okay. Dispersion forces or London forces. It operates for a short distance and it is the weakest. Okay. But London, as we read previously, London forces are quite strong in liquids and solids. And the factor between those decreases by a factor of 1 upon r cube when they are separated per unit distance. It operates for a short distance and it is the weakest. The kind of force arises due to the movement of electrons, thus creating temporary positive or negative charged regions. Okay, got it. So this London forces is quite an interesting case. So let's look at the weird cases of London dispersion forces. Okay, so we are now in the relative magnitude section of the London dispersion force page of Wikipedia. Dispersion forces are usually dominant over the three van der Waals forces, that is, orientation, induction, dispersion between atoms and molecules, with the exception of molecules that are small and highly polar, such as water. The following contribution of the dispersion to the intermolecular interaction energy has been given. Okay. Ne pair 100%, CH4 CH4 100, HCl 86, HBr is 96. But I think we read that. Okay, that was Br2. So Br2, I think, is a liquid at room temperature, and it has quite a strong London dispersion forces between them. CH3Cl, CH3Cl68, NH3, NH357, water 24, hydrochloric acid, HI as 96, water and methane adds 87. Okay, so these are the relative magnitude. Yeah, so quantum mechanical theory is given and a distance factor of r raised to 6 is given in the equation. The London theory has much similarity to quantum mechanical theory of light dispersion, which is why London coined the phrase dispersion effect. In physics, the term dispersion describes the variation of a quantity with frequency, which is the fluctuation of the electrons in the case of London dispersion. Okay, so let's look at the valence atoms. Uh, Valence atoms of an element. In chemistry, the valence or valency of an atom is a measure of its combining capacity with other atoms when it forms chemical compounds or molecules. Valence is generally understood to be the number of chemical bonds that each atom of a given chemical element typically forms. Double bonds are considered to be two bonds, triple bonds to be three, quadruple bonds to be four, quintuple bonds to be five, sextuple bonds to be six. In most compounds, the valence of a hydrogen is one, oxygen is two, nitrogen is three, and carbon is four. So valency basically is like the combining or interacting capacity of a given molecule or an atom. For example, for hydrogen it is 1, oxygen has it's 2, nitrogen is 3, carbon is having 4. Valence is not to be confused with the related concepts of the coordination number, the oxidation state, or the number of valence electrons for a given atom. Okay, so valence is different from valence electrons. The valence is the combining capacity. Yes, as I said, the valence is the combining capacity of an atom of a given element determined by the number of hydrogen atoms that it combines with. In methane, carbon has a valence of 4. In ammonia, nitrogen has a valence of 3. In oxygen, in water, the oxygen has a valence of 2. And in hydrogen chloride, chlorine has a valence of 3. In phosphine, pH 3 and valence of 5. In phosphorus pentachloride, which shows that the element may exhibit more than one valence. The structural formula of a compound represents the connectivity of atoms. The two tables below show examples of how different compounds, their structure formulas, and the valences for each element of the compound. Hmm. So basically, I think valence is like a number which represents the combining capacity, as in with how many other different or same atoms or molecules that compound can or atom can interact with. For example, here it is shown that hydrogen has 1. Here carbon has 4. Like carbon again has 4. So okay, so each carbon has 4. Here again 4. Here again 3 plus 1 4. Okay. So the IUPAC definition is defined as the maximum number of univalent atoms, originally hydrogen or chlorine atoms, that may combine with an atom of the element under consideration or with a fragment, or for which an atom of this element can be substituted. An alternative modern description is the number of hydrogen atoms that can combine with an element in a binary hydride, or twice the number of oxygen atoms combining with an element in its oxide or oxides. Okay, so this definition is pretty clear now. So let's move to know about what exactly is titration. Okay, so let's click on the chemistry library site. Titration is the slow addition of one solution of a known concentrated of a known concentration called as titrant to a known volume of another solution of unknown concentration until the reaction reaches neutralization, which is often indicated by a color change. The solution called the titrant must satisfy the necessary requirements to be a primary or secondary standard. In a broader sense, titration is a technique to determine the concentration of an unknown solution. So yeah, so this is pretty mathematical. Basically, we take an unknown quantity of a solution and then mix it with a titrant of unknown concentration and volume, and we slowly add it to the unknown volume of the unknown volume of the given compound until it reaches the neutralization state, which is often indicated by a color change. Okay, So there are acid-base titrations, precipitation titrations, titration of a strong acid with a strong base, titration of a weak base with a strong acid, complexation titration, redox titration, titration of a weak acid with a strong base, and titration of a weak polyprotic acid. Polyprotic acid is an acid that is usually considered as weak acid in its monoprotic form, but instead has more than one H plus in the molecule, therefore making it polyprotic. Okay, so polyprotic means I think multiple hydrogen loving acid. Okay, so the idea of titration is also clear. Okay, got it. So now let's move to a chemistry practice question set. And yeah, so now let's move to the chemistry practice questions. A molecule with five carbons must always be called as, so it will always be called as, mm, pentanone. It will have the pentane prefix, but it will have a pen prefix that represents the number 5. But we need more information whether it has having some special group or like what is its diagrammatical structure represented as. So not enough information. In regards to naming the numbers assigned to each carbon atom in an organic molecule, usually must be the dash possible. In regards to naming the numbers assigned to each carbon atom in an organic molecule, usually must be the. So we will come back to this question. Let's move to what is the formula for the number of hydrogens in an alkane. So alkane has 2n plus 2. Esters and carboxylic acids can be thought of opposites in what regard? Structures, one contains two oxygens, another only one. Size, carboxylic acids are always larger than ester. Reactivity, carboxylic acids are inert while ester combust in contact with air. Odor test, carbolic acid test, sour while ester smells sweet. Usefulness, esters were created for no reason why. So I think in odor and taste, carboxylic acids are sour while esters are smell sweet, as we read. LDFs can be stronger than H bonds when the molecule with only LDFs. LDFs is London dispersion forces is sufficiently dash than the molecule with dash bonds. Can be stronger than H bonds when the molecule with only LDFs is sufficiently dash than the molecule with H bonds. Hmm. LDFs can be stronger than H bonds. Okay. Uh, LDFs can be stronger than H bonds when the molecule with only LDFs is sufficiently dash than the molecule with H bonds. So, uh, I think if it is larger, because I think more the number of atoms present in the molecule. So then, if it is larger in size, or then it will be sufficiently stronger than the H bonds. So I think it should be larger. Carbon can make a maximum of dash bonds and theoretically a minimum of dash bonds. Separate your answers with a comma, then a space. Hmm. So the valency of the carbon is, I think, 4, but it is also asking a theoretical minimum. So carbon can make a maximum of dash bonds and theoretically a minimum of dash bonds. Separate your answers with a comma, then a space. Okay. So valency is 4 and minimum bond I think it can make is Mm-hmm. But uh, carbon, I think, can exist without a bond, right? So can make a maximum of dash bond and theoretically a minimum of dash bonds. Okay, so in the first part for maximum bonds, it is asking for what happens in real life, and then for the theoretical minimum, it is asking for the theoretical number. So I think maximum a carbon can make is four bonds, and minimum it can make is I think no bonds, that is zero bond. The presence of an alkene can be tested for by first adding. Okay, the presence of an alkene. The presence of an alkene can be tested for by first adding water, bromine, another alkene, an alkane, or benzene. Hmm. So alkene is also, I think, a type of hydrocarbon, and I think it is bromine because bromine is, I think, is a coloring substance. So let's go with bromine. The presence of an acid can be tested for by first adding. By first adding. Hmm. Cabbage. I think it is not. An electrode. An electrode will basically, I think, dissociate that acid. A base will neutralize the acid. Water will basically dilute the acid. And salt, I have no idea what it will do. But uh, the presence of an acid can be tested for by first adding. Cabbage, electrode, a base, water, or salt. Uh, so cabbage cannot be the correct answer. Mm, a base. Hmm. But I think presence of an acid. So acid is basically they are basically corrosive in nature, right? So cabbage is like a natural thing. It's a vegetable. So if I pour acid on a cabbage, the cabbage's color or might change, or maybe the it will cause damage to a cabbage. So let's go with cabbage. Despite ethanol being smaller than butane, it has a higher boiling point due to. Despite ethanol being smaller than butane, it has a higher boiling point due to. Hmm. Ethanol is basically an alcohol and butane is an alkane. So, despite ethanol being smaller than butane, it has a higher boiling point due to being harder to metabolize, its ability to participate in hydrogen bonding, its lower number of hydrogen atoms, its smaller size, or a large amount of LDFs. I think ethanol has a simple structure, so it might not have a large amount of LDFs. Otherwise, as we have read that more the LDF, the higher will be the boiling point. Hmm. Has a higher boiling point, I think, because of its ability to participate in hydrogen bonding. That is the polar nature. That is why. Okay, so let's go with this. So let's submit it. View score. Mm. Lowest or smallest? Okay, so this I got wrong. All molecules contain carbon or organic molecules. So this was false. I think we missed this question. Okay, the presence a base. Okay, so cabbage was wrong. Okay. Mm. Mm. The lowest. Okay, so the number of parent chain should be higher, but the number assigned to each carbon should be lowest. Okay, got it. Okay. So now let's move on to the post test and test ourselves how we do in this. Okay, use this diagram to answer the following 7 questions.